Okay, thank you. So, next talk, Traceable mixnets. Over to you.
Thank you very much. Hi, my name is Prashant, and I will be talking about this new cryptographic primitive we have introduced in this paper called Traceable mixnets. This is joint work with all these nice people. One of them you'll find somewhere here. So the agenda today is I will introduce traceable mixnets and contrast that with traditional mixnets. And then I'll go over the key challenges in building traceable mixnets, the key techniques we use, and some comparisons with existing techniques. And then I'll talk about applications of traceable mixnet in the context of voting, in particular how to recover from failures in large elections. A mixnet is a primitive used for anonymous communication. In particular, it takes as input a list of ciphertexts which encrypt some sensitive content like a vote in an election. And the ciphertexts are usually tagged with some metadata information about the sender. For example, the identity of the voter or the place, the booth they are voting from. And the mixnet actually is, it consists of multiple mix servers. Here I am just showing two, M1 and M2, which successively permute the list of ciphertexts and finally produce a permuted decryption list. And the guarantees that it provides is it's verifiable, that it can prove that the output list is indeed a decryption of a permutation of the input list of ciphertexts. But also mixnets are completely untraceable, so that assuming that at least one honest mix server exists, the association between the ciphertext and the plaintext cannot be identified at all, and it is completely untraceable. So untraceability is indeed a gold standard, but sometimes in some applications some form of controlled traceability is also required, and this is what is the focus of this paper. And we formalize this controlled traceability in the form of special queries that we call trace in and trace out queries. So let me just explain what I mean by trace out. So a trace out query takes as input a plain text in the output list of the mixnet and a set of ciphertext in the input list of the mixnet, and answers the question whether the plain text was encrypted in one of the ciphertexts in the input list without revealing which ciphertext indeed. And this gives you a proof of provenance of the plain text item. And symmetrically, a tracing query takes in ciphertext from the input list of the mixnet and a set of items, a set of plain text items from the output list, and answers the question whether this ciphertext encrypts one of the items in the set without revealing which one. So this is a form of proof of eligibility or membership of the ciphertext of the sender. And the main challenges in giving these kind of answering these queries is verifiability. And the mixnets have to verifiably answer these queries and not just know the answers to those queries themselves. They have to prove it to a verifier. Secrecy, no additional information apart from the output of the query should be revealed. And what makes this kind of proof very difficult is because this is a distributed proof, so none of the mix servers by themselves know the association between the ciphertext and the plaintext, yet somehow jointly they should prove statements about it, and that makes this challenging. And finally, what we are after in terms of efficiency is batch efficiency, which means that if you run multiple such queries, for example, a traceout query, if you run multiple of them against the same set, then we want such batched executions to be efficient. And as you can perhaps imagine, a naive repetition of multiple traceout queries could be quadratic in the size of the mixnet input list, but we want the entire batch query to be linear. So a traceable mixnet is essentially, these are mixnets that address these challenges precisely. They are mixnets that provably answer batched trace-in, trace-out queries efficiently, which means linear in the size of the input list, and without leaking any additional information. So before I go further into the construction of traceable mixnets, I want to spend a minute into what are the secrecy properties of traceable mixnets, especially in the presence of these additional queries, and how they should be deployed. And of course, because we support these additional queries, they leak more information than a completely untraceable mixnet. So what queries to be allowed should be decided at an application level, depending on the application level secrecy requirements. Given a set of queries, there should be a privacy risk analysis step which identifies what is the privacy risk with allowing these set of queries. And we give some framework in the paper. After this analysis, query access policy should be decided, which decides who gets to execute what queries. And the traceable mixnet basically guarantees that the query access policy will be faithfully followed. In particular, what we guarantee is that no query is answered unless all mix servers agree to answer it, which prevents against bad queries. The querier doesn't learn any more information beyond the output of the query. This last one says that the mix servers don't even learn the query output. So in this sense, the mix servers answer the query obliviously. And this is required to prevent mix servers from accumulating query responses given to different queryers over time, and then completely learning the link between ciphertexts and plaintexts. But this property prevents against that. Okay, so now let me describe some key techniques behind our construction. So the tracing query is enabled by a popular zero-knowledge proof in cryptography, which is called zero-knowledge proof of set membership. This is a proof that takes a commitment as an input and a set of plaintext values as input, and answers and proves whether the commitment commits some value in the set phi without revealing which value it commits. And this is a well-established proof. We in fact give another zero-knowledge proof, which we rather uncreatively call zero-knowledge proof of reverse set membership. So a ZKP of reverse set membership takes a plaintext value and a set of commitments as input, and proves whether some commitment in this set commits the value without revealing which commitment. So the traceout query is based upon the ZKP of reverse set membership. And so far, these are single prover proofs in the non-batched setting. So one important extension in the paper is how to make them distributed and how to create batched versions of these zero-knowledge proofs. Unfortunately, I will not have time to go over how we make that construction, but I will provide you some comparisons with existing techniques in the literature. In particular, we compare with respect to three main metrics. What is the complexity of giving the batch proof, and whether the technique supports reverse set membership, and whether it supports single prover or distributed provers. So the first technique that may come to your mind is the standard OR composition of sigma protocols, where you can prove that a commitment commits a value in the set by proving that it either commits the first value or the second value or the third value and so on. And you can imagine that for a batch proof, this will be quadratic overall. This supports reverse set membership also because it's a generic technique, but unfortunately this is only a single prover technique. Similarly, you can use ZK snarks and Merkle accumulators, which provides order n log n complexity for a batch proof. And since again this is a generic technique, supports reverse set membership, but it is a single prover technique. There was this interesting approach by Kamenish et al. In 2008, where the proof that a commitment commits a value in the set involves proving that I know a signature on the committed value. One proof was order 1, which gives an order n complexity for a batch proof, but this was an interactive proof. And since this was a specific technique, it doesn't support reverse set membership, it was only for set membership. We actually extended for reverse set membership, and this was also a single prover technique. So, in the setting of distributed provers, there was recently work on collaborative ZK snarks, which generically extend ZK snarks. It retains the asymptotic complexity of ZK snarks, and this is our main comparison point. We actually extend from the signature-based set membership proof technique and add support for reverse set membership and make it distributed. And in terms of comparison with collaborative ZK snarks, our technique is 86 times faster set membership proof and 18 times faster reverse set membership proof. And the implementation is completely available in this link. Alright, so now let me come to the application in terms of failure recovery in elections. So in elections, usually a typical scenario is that voters go to cast their vote and their encrypted votes are at the beginning of the mixnet, which may contain information about which booth they voted at and so on. And the mixnet permutes and decrypts the votes. But asking for a large election, asking the election authority to completely rely on cryptographic voting is very hard sell. So it is often also required to maintain a paper audit trail where paper votes are also separately kept. But now we have a problem, because if there is a mismatch between the electronic votes and the paper votes, then you cannot resolve these disputes. And because of the untraceability property of mixnet, you can't even identify where these failures originated from. So in fact, this is what we do with a traceout query. You can actually consider the set of votes that were cast at a particular booth and then answer whether this discrepancy was originated in that booth, without revealing any additional information, specifically without revealing which voter it corresponds to, and without even revealing the booth level voting statistics. And we present more sort of similar recovery use cases in this paper, which was published in eVote ID 2023. And this is, so the traceable mixnet enables these kind of generic localized recovery use cases. So that's all I had to say. I'm open to any questions.
Hi, great work. I was just curious, you said at the beginning that you need to establish what queries you're allowed to set. So I guess in the setting of this election is quite clear, because there's one election council and they decide what queries. But say you have like a system where your aim is not about verifying like elections, like you just say sending emails, right? So at some level, all the users or someone has to decide what sort of, for example, the size of the set that you're allowing, right? Because you just have one as well, and you'd be like, well, it's not in the set, it's just this particular entry, and then maybe you de-anonymize someone because of that reason, right? So I'm just curious, like, do you think it's like what practicality there is in trying to establish these query sets, and how you might go about doing that?
Yeah, I think that completely depends on the application. And in the case of voting, it depends on where failures happened and which booths you suspect and so on. So it is very application dependent. But yeah, so you have to do that application dependent privacy analysis.
Right. Thank you to the speaker.